Welcome to Sweet Spot Maths, the gold standard for A-level maths teaching. I'm David Forster. In this video, I'm going to continue going through, as revision, the Edexcel paper 1 from 2020, and I'm going to cover questions 6 to 9. Question 6 is another modelling question. We're asked first of all to express sine x plus 2 cos x in the form r sine x plus alpha. This is a standard technique. We're asked to give the exact value of r and the value of alpha in radians to 3 decimal places. So we write sine x plus 2 cos x as r sine x plus alpha, expand the right-hand side using the sine a plus b formula, then comparing the two sides. On the left-hand side, there's 1 sine x, and on the right-hand side, r cos alpha. So 1 equals r cos alpha. And likewise, comparing the coefficients of cos x, we get 2 equals r sine alpha. Using Pythagoras, we find that r is the square root of 1 squared plus 2 squared, the root of 5. We're asked for an exact answer, so we leave it like that. Dividing one by the other, we get tan of alpha is 2 over 1, which is 2. Inverse tan of 2 in radians, 1.107 to 3 decimal places. So we have root 5 sine x plus 1.107. Strictly speaking here, it does ask us to express it in the form r sine x plus alpha. So we don't just want to write down what the values of r and alpha are. We do actually want to do what the question has said. Next part, this is where the modelling comes in. The temperature theta degrees C inside a room is given by this equation. So this is very similar to part A. We have a 5 plus, and then we have sine of something, add 2 cos of the same thing. So that in brackets is the theta from the first part, or the x from the first part, I should say. So, using the equation of the model and your answer to part A, deduce the maximum temperature of the room during the day. So, we have 5 plus, and we replace the second part using the formula from part A as root 5 sine of, instead of x this time, it's pi t over 12, take 3 plus alpha, which is 1.107. We want the maximum value of theta. The fact we want to use here is that the maximum value of sine of anything will be 1. That's when the thing inside the brackets, the value inside the brackets, is pi over 2. So the maximum value is 5 plus root 5 degrees C, or 7.24 degrees C. Either will do here as an answer. We're now asked to find the time of the day when this maximum temperature occurs, giving the answer to the nearest minute. So we just said that the value inside the brackets must equal pi over 2. So we set it as pi over 2 and rearrange and get 13.23 hours. So we want the time. It's the time after midnight. So it's 13 hours. 0.23 of an hour is 14 minutes to the nearest minute. So it's 13:14 in the 24-hour clock, or 1.14 p.m. would be okay as well. So just to emphasize, deduce in part B means use part A. And we don't want here really to head off in another direction, for example, by differentiating to find the maximum. That would in fact give the correct answer, but is long-winded and unnecessary. Thinking like a mathematician, using the fact that the maximum value of sine of anything is 1 is a useful thing to know and to use. Okay, so on to question 7. Figure 1 shows the sketch of a curve C with equation y equals fx and a straight line L. The curve C meets L at 2 points, minus 213, and 0.25, and we have a shaded region R in between, which is bounded by the line and the curve. Now, seeing this, we might immediately think we're being asked to find the area of R using integration, but in fact we're not here. We've been asked to do something different. So we're given that f of x is a quadratic, and minus 213 is the minimum turning point. And the question is to use inequalities to define R. So for the straight line, we know 2 points it goes through. It goes 2 across and 12 up, which means the gradient is 6 and the intercept is 25. So we get the straight line y equals 6x plus 25. Do make sure when you're giving the equations of lines that you include the y equals. Quite a common mistake is to write down L equals 6x plus 25 or just 6x plus 25. For the equation of a line, you do need the y equals as well. The equation of the quadratic, a little bit harder. Probably the easiest way of doing this is to write it in the form of ax plus 2 squared, add a constant. And the reason is we know that the vertex, the minimum turning point, is at minus 2. So the quadratic has got to have in it x plus 2 squared. It can be multiplied by a constant, which is going to be the coefficient of x squared. And we need also a constant as well. The constant will be 13 because when x is minus 2, the y value is 13. We can write down straight away that the equation of the quadratic is of this form. Then use 0.25 to find the a value. 25 equals 4a plus 13, so a is 3. Here's the equation of the quadratic. You can leave it in this form. You don't need to multiply it out into ax squared plus bx plus c in this question. So region R is going to be, the y values have got to be bigger than the quadratic and less than the straight line. So here is one way of writing the answer. You are allowed to use a less than, a strictly less than, or a less than or equal to sign, but the mark scheme does say that you must be consistent. That is, that you must use either one or the other in both places. This is one region we're looking at, so we do want it written in one part, not as two parts with an or between them. Now, it is instructive, I think, to look at the mark scheme here and see what it says. A very significant majority of the candidates did not seem to know how to define a region using inequalities. It was common to see a response where the area of region R was attempted using integration. Only a small minority of candidates who made a correct inequality statement at the end. It was often the case that the final mark was lost due to a candidate using the letter R rather than Y in their inequality. So this is one of these questions where many candidates did not get it right. So those of you following the Sweet Spot Maths program, you will know we try to make these areas of weakness in other candidates our strength to give us the examination edge. So moving down the mark scheme, the examiner's report says the line equation correctly was achieved by most candidates. Finding the equation of the quadratic curve was found to be more difficult, a common error being to neglect the a, the constant, in front of x plus 2 squared. So once again, doing questions of this sort and making sure you can get them right should give you an examination edge. Okay, on to question 8, which is worth only 2 marks. A new smartphone was released by the company, which monitored the total number of phones sold, N, at time T days. The company observed that the rate of increase of N was proportional to N. Use this equation to write down a suitable equation for n in terms of t. So we're told the rate of change of n with respect to t is proportional to n. In other words, dn dt equals kn. For a positive constant k, it's an increase. Now, hopefully you will recognize that when you have a situation where the rate of change is proportional to the value itself, to n, we are going to get an exponential situation, n equals ae to the kt. And you can simply write that down as your equation, your final answer. A and k do not need to be evaluated. In fact, we can't evaluate them. We have no information. You could have done this by solving the differential equation, but in fact, you don't need to do that. You are allowed to recognize in these questions that it will be an exponential model. You need to have both the constants a and k in here for full marks. So worth only 2 marks. Let's go back to the mark scheme and see what it says about this question. Candidates were expected to realize that when a rate of change is proportional to the y value, the exponential model should be used. The question seemed to take a great many candidates by surprise. Those who did interpret the situation correctly could write down the equation very quickly, whereas others attempted to solve a differential equation. So, although this is only worth 2 marks, a lot of candidates didn't get those marks. So once again, something to make sure you can do when you face that examination. The final question I'm going to cover in this video is question 9. We're given the sketch of a curve C with equation y equals fx, where f of x is 4 times x squared minus 2 times e to the minus 2x. So you can see the graph here behaving very differently on the left-hand side to the right-hand side. We're asked to show that f dashed of x is the thing given here. Remember, f dash of x is just another way of saying dy dx. The obvious way of doing this is to use the product rule, although you could use the quotient rule with e to the 2x on the bottom. It's a show that question, so you do need to show all the steps clearly. So product rule with u is 4 times x squared minus 2. du will be 8x. And using v is e to the minus 2x, dv will be minus 2 e to the minus 2x. Putting those bits together, u dv plus v du, we get this. And that factorizes to put e to the minus 2x outside of brackets. And then we get 8 times 2 plus x minus x squared as required. Part B. Hence find in simplest form the exact coordinates of the stationary points of C. I do recommend you do as I've done here and underline really important words like hence and simplest and exact. They are things we need to make sure we do them to get full marks. Hence means use the previous answer. Let's do that. So we have f dash of x is 0. The answer to the previous part is 0. 8 clearly isn't 0. And also e to the minus 2x cannot be 0. So we have the quadratic 2 plus x, take x squared is 0, which solves to give x equals minus 1 or 2. You can see on the graph those two turning points, a minimum turning point when x is minus 1 and a maximum when x is 2. We need to find the exact coordinates, that's the y value as well, and it needs to be in exact form. So taking x equals minus 1 and putting it into the formula for y gives minus 4e squared, that's exact. Putting 2 into the formula for y gives 8e to the minus 4, and that's exact. And it's the simplest form. Now, part C is somewhat different. We've been given two functions, gx and h of x, which are defined in terms of the original function f(x), and we're being asked to find the range of these two functions. So first of all, g equals 2f of x, same domain, real numbers. So the original function f of x, its range is that y is greater than or equal to minus 4e squared. So the range of g of x, when we double it, is that y will be greater than or equal to minus 8e squared. Answer given. Now there's a potential trap in part 2. The range of h of x is 2f of x, take 3, which is the first part, g of x take 3, but the domain has been changed to x is greater than or equal to 0. We're only defining h of x on the right hand side, so I need to know the range of the original function f of x on the right hand side. It's different to the range for the whole of the real numbers. So the range of fx will be from the intercept up to the maximum turning point. In other words, the range of fx in this part is going to be from minus 8 up to 8e to the minus 4. So for h of x, we simply multiply by 2 and take off 3. So minus 8 times 2, take 3 is minus 19. 8e to the minus 4 times 2 take 3 is 16e to the minus 4 take 3. Let us look again at the examiner's report and see what they say about this question. So back to the report. Parts A and B were standard bookwork involving the product rule of differentiation using an exponential function. Well-rehearsed candidates were very successful here in getting the majority of marks. Unsurprisingly, candidates found Part C more challenging, especially C Part 2, where the significance of x is naught was rarely understood. In other words, candidates did not spot that condition that x has to be naught or greater. However, this part of the question was a good discriminator for stronger candidates. That means if you see yourself as a stronger candidate, this is a good thing to look at and practice. In other words, you're working in the sweet spot and gaining the examination edge by doing questions like 9 Part C, Part 2. That's it for this installment of the video. In the next part, I will go on to question 10 and beyond. This is Sweet Spot Maths, the gold standard for A-level maths teaching. I'm David Forster. We're doing maths in the sweet spot, which is fine-tuned to achieve A star directly without wasting time. We're shifting our perspective, learning to think like mathematicians and complete even the hardest exam questions correctly and confidently. And we're learning those examination secrets, the gaps, mistakes and omissions of most candidates, which will give us the examination edge, a competitive advantage. If you would like to know more about Sweet Spot Maths, email me at support@davidforster.org.uk and I'd be delighted to send you further information. Thank you for listening to this video.